I want it to have very small support, so C0 will be very small. And I'm going to define a function that counts low-lying zeros. So let me introduce definition df psi. So I want to sum over all zeros, gamma. So gamma are all real numbers. So L of a half plus I gamma f equals 0. And then I'm going to take psi of gamma log CF over 2 pi. So I have to tell you what CF is. So if you have a family, you can usually get an asymptotic formula for NTF. And the asymptotic formula will look like NTF is asymptotic to T log CF T as T goes to infinity. So this will be the, you can really prove this kind of thing. Okay? If you have a real family, we can prove this by the same way you can for the Riemann zeta function. I think CF is 2 pi for the Riemann zeta function. CF is called the analytic conductor of F.
1 by 2 pi.
What? Is it 1 over 2 pi? I don't remember. It might be 1 over 2 pi. Yeah. This is, since psi has very small support, this is just counting the low-lying zeros, this sum. It just counts low-lying zeros. So if we can estimate, if we can get an asymptotic formula for this sum, then we know how many zeros there are close to 1/2. So now here is the conjecture. So this is Katz and Sarnak. Let me take the limit as t goes to infinity of this sum of so I have to define f of t. So f is my family, and f of t is going to be the set of all zeros, gamma. It's going to be the set of f and f such that CF is less than or equal to t. Okay, I'm going to, f of t is just that. So I want to take 1 over f of t, the number of elements in f of t, and then this sum, and then the sum of df psi. df psi. And I want to take the limit as t goes to infinity. Okay, so in some sense, I'm counting the average number of low-lying zeros for all the L functions in the family. And the conjecture says that this is given by an integral from minus infinity to infinity, psi of x times w, where w depends on the family, dx. And Sarnak and Katz conjectured that this w, there are only 4 possible w's that can occur, no matter what the family is. And I will tell you the 4 possible. What? For any t, it'll be finite. For any fixed t, it'll be finite. Yeah. If you have the wrong definition of family, it could be infinite. Yeah, so we have to make sure that define family, so that's finite. Yeah. So let me now tell you the possible things that W can be. The conjecture is there are only 4 possible W's that can occur. So if you pick a family, different family might have different W's, but only these 4 can happen. It's really surprising. I mean, you would think that you could get anything here. I mean, but apparently these are the only 4, and the reason is that zeros of L functions in a family, should behave like eigenvalues of a random matrix in a classical group. So asking for zeros near a half is the same as asking for eigenvalues near the identity, near 1. And the 4 classical groups, so delta 0 is the Dirac delta function at the origin. This is the orthogonal group, ON. This is the SO2N, the special even orthogonal group. And this is SO2N plus 1. And this is the symplectic group, SP of 2N. So if you consider the problem of you take one of these 4 classical Lie groups, you randomly pick a matrix inside the group, and you ask what is the distribution of eigenvalues near the identity, it will have these distributions. So this is the conjecture. So what is known about this conjecture? Well, at the moment, not much is known. I can tell you for which families this conjecture has been proved. So the first result was in, I think it was 2003. So it's Ivaniech, Luo, and Sarnak proved the conjecture for the family of holomorphic modular forms of weight k. And the symmetric square lift of these. Okay. And so the symmetric square lift, they got symplectic type, SP. And I think For the automorphic forms, it's orthogonal type. There's two different symmetry. So these groups are called the symmetry type. So this was really the first result in this direction. It was a very long paper in the publications of IHES. And just recently, last month, Steve Miller and 4 other people whose names I can't remember also generalized this result to mass forms for GL2. So in 2011, they generalized this to mass forms for SL2Z. And basically, that's all that's known. That's all that's known. So what I want to show today is that we can also get this kind of result for the group GL3. So this is the first time that someone got a symmetry type for a group with rank bigger than 1. So since I was told that not everyone is GL3, I'm going to give a very elementary introduction to GL3. So, I'm going to explain what the family is and then state the result that we can get. So probably the best way to do it is to take something familiar, which is GL2, and then compare it with GL3. So on the left side, I will have GL2, which I hope is familiar to people here. And on the right side, I will tell you what happens on GL3. So the first thing that, if you have a modular form on GL2, it lives on the upper half plane. So I call the upper half plane H2. Of course, classically, it's the set of x and y is greater than 0. But there's no analog of this on GL3. We have to work in the group setting. But this is isomorphic to the following. It's isomorphic to the set of matrices 1x01 times y001, which is, of course, yx01, where x is an R and y is greater than 0. These matrices, it's the same thing. If you do this act on I, you get x plus iy. So that's the way we think of the upper half plane. And now, what is the analog on the GL3 side? On the GL3, so I call such an element Z. So Z is yx01. It's an element of H2. So it's a matrix. I have to think of it as a matrix. Here, Z will look like this. It's 1, x1, x3, 0, 1, x2, 0, 0, 1, y1, y2, 0, 0, 0, y1, 0, 0, 0, 1. This is my Z. This is the analog. And here, x1, x2, x3 will be real numbers. And y1 and y2 will be greater than 0. Upper half plane is a two-dimensional space. I mean, you have x and y. You have two things that, 2 dimensions. This is a 5-dimensional space. No complex structure here. You can't, there's nothing analogous, there's nothing like an upper half plane in the classical sense. So now I want to talk about modular forms or automorphic forms. So let me talk about automorphic forms, weight 0. I don't want to get involved with CZ plus D to the K power. So we fix groups. is SL2Z. So SL2Z acts on H2 by left multiplication. So if you have ABCD sitting inside here, you can and that will give you an action. It's just left multiplication. And an automorphic form is a function phi that satisfies phi of gamma z is equal to phi of z for all gamma in gamma and z in H2. So this is basically what an automorphic form is. It's a function that satisfies this kind of condition. So if I would put in a weight, I could talk about modular forms, but I don't want to talk about the weight today. So it makes it a little more complicated. And there's one other thing that comes into it, the Laplacian. So there's an invariant differential operator under this action, and that's the Laplacian delta, which is minus y squared d squared dx squared plus d squared dy squared. That's the Laplace operator. And so this is the first condition. The second condition, this function should be an eigenfunction of the Laplacian. So it should satisfy del phi is lambda phi. So these are the two conditions. Okay, so this whole theory was worked out in a paper of Moss in the 1940s. So and these are now called Moss forms. Here's the analog here. So here I'm going in the simple. I work with other groups. You could take a congruent subgroup, but I want to take the simple example. So let me here will be SL3Z. 3 by 3 matrices, integer coefficients, determinant 1. And a function, an automorphic form, is a function phi from this upper half plane to C that satisfies similar conditions to this. So the first condition is that phi of gamma z should be equal to phi of z for all gamma in gamma. So that's the first condition. We also have a Laplace operator here on this space. It's much more complicated. It'll be some operator in ddx1, ddx2, ddx3, ddy1, ddy2. And it'll have cross terms, and it's so complicated that it's in my book, but if you want to see what it looks like, it's not very nice. It's a big mess. Anyway, so the second condition is that del phi is lambda phi. So it's exactly the same, yes? It's the Casimir operator. It's exactly the Casimir operator. It's in the center of the universal enveloping algebra. So to construct this operator, you have to use Lie theory. On L2, you can construct it pretty easily with just by getting your hands on it. I mean, if you know the action of d, it's like ddz times ddz bar times y squared, something. It's very easy to get it, but on GL3 and higher rank groups, you really have to use Lie. So as he said, it's the Casimir operator. Okay, so Ivanich and Cernak looked at a family of forms something like this on GL2. So it's natural to look at a family here. So we have to discuss what is the L function of such an object. We want to attach an L function to each such object. So let me explain how to do that. Again, I will do it for GL2 and for GL3 separately. So let me talk about L functions. So on this side, I will put GL2, and on this side, I will put GL3. So we note acting on yx01. This is in SL2Z, so this has to be the same as phi of yx01, right? Because condition. So this has to be true. But if you multiply these matrices, you see that this is phi of yx plus 1, 0, 1. So that means phi, if we fix y, then phi of z is periodic in x. So it has a classical Fourier expansion. So phi of z looks like summation an, but the coefficient could depend on y, you see. And then e to the 2 pi I n x. So that follows immediately just from knowing that it's invariant under 1101. But then we know that it satisfies a differential equation. So that means each Fourier coefficient satisfies a differential equation. Therefore, you can then, if you work it out, you see that the an of y satisfies a second order differential equation of y. And it's exactly the differential equation of a Bessel function. So it relates to the K Bessel function. So if the eigenvalue, if this eigenvalue lambda is 1/4 plus t squared, the eigenvalue is 1/4, let me write it that way, then we see that phi of z has an expansion of the following type. So it'll be a constant an that doesn't depend, this is just a constant, and then there will be square root y, and then the K Bessel function, kit of 2 pi and y, and then e to the 2 pi I n x. Anyway, this is a computation. You can find it in many, many places. No, this is a different an. Let me call it capital An. Okay, but it's a constant. For each n, it's a constant. And then we can attach an L function to phi. So I'll put the definition here. The L function, Ls phi, associated to phi, is defined to be the sum n goes from 1 to infinity, an over n to the s. And we usually normalize it so that a is 1. Otherwise, it's not. We usually normalize it that way. There are other ways to normalize it, but that's the more standard way. So that's how to attach an L function. And because this is an automorphic function, you can then prove all the properties, functional equation, analytic continuation, they all follow by the proofs are exactly the same as for the Ramanujan. The exact same proofs. Everything works. Okay. All right, let me now look on the case of GL3. In the case of GL3, things change quite a bit. So the first thing you can do is ask for this kind of thing. So I could take something like phi of 1, 1, 0, 0, 1, 0, 0, 0, 1, 1, 1, 1, x1, x2, x3. I could pick like that matrix. So this is, of course, going to be the same as phi of z. Z is this piece, because this is an SL3 invariant. But if you multiply the matrices, what are you going to get? You're going to get phi. This is going to be 1. This is going to be x1 plus 1. You see, right? This changes in some funny way. It's x2 plus x3. This is 1. This is x2, and this is 1. And this is 1, 1, 1, 2. So it's not quite periodic, right? It's not quite periodic. I mean, I think you'll get a better result if you do 1, 0, 1 or something. I mean, so it's not quite periodic. There's a problem. It's almost periodic. The problem is that this upper group is not an abelian group. If you look at the upper triangular group, it's not an abelian group. And so you can't use standard methods of Fourier theory. So it's not at all obvious what to do. Okay? This function, by the way, is called a Whittaker function, this whole function, and it's usually written WIT of z. Okay? It's called a Whittaker function. But let me tell you what's known. So the analog of the Fourier expansion was proved independently by Shalaika and Piatetsky-Shapiro. And let me tell you what they proved. That phi of z has an expansion of the following type. This is just a normalization coefficient. You see, I could slightly change it. I could put an n here and divide by square root n. So you get 1 over square root n. So that's the analog of the normalization coefficient. And then there's a sum over gamma in SL2z modulo gamma infinity, where gamma infinity are the elements that fix infinity, the elements of the form 1, n, 0, 1. The usual, this sum is how you make an Eisenstein series on GL2. You sum this way. And then you have the Whittaker function. It depends on two variables, IT1 and IT2. Instead of one variable, there are now two variables. And then inside, it's rather complicated. M1, M2, M1, 1, gamma 1, Z. And this function is a log of a K-Bessel function. It has similar properties. So this was what they proved. This is not so easy to prove. It's proved in my book. And now, associated to this, we can attach an L function. And what's surprising is that the L function is defined this way, A1m over m to the s. It's surprising that it's defined that way. But this is the correct option. And this, if this function is an eigenfunction of the Hecke operators, this has an Euler product. It will be a degree 3 Euler product. All right, the next thing I want to talk about is the Rankin-Selberg convolution. So here we have Rankin-Selberg on GL2. We have Rankin-Selberg. L function. So, so this is LS phi. And then we have LS phi cross phi, which is defined to be, it's the sum of the squares, an squared over n to the s. So this is the Rankin-Selberg L function. And this, it's well known that this is a nice function. Satisfies the nice properties. Vivanius, Luo, Sarnak, they look at the family of Rankin L functions on GL2. They're actually looking at a holomorphic family. Recently, people look at a family of non-holomorphic forms. And they established the symmetry type for the low-lying zeros of this family. So we want to do the same thing here. So the question is, what is LS phi cross phi? And what's it turns out to be that it's now a double sum. So if you imagine that you are trying to discover this by yourself for the first time, you would never think of that. I mean, you might say, what about this function, a1 n squared over n to the s? Unfortunately, this function doesn't seem to have any nice properties. I believe it has a natural boundary even. This is not a natural function. This is the correct, these are the correct objects. Now remember, we are looking at this from a classical point of view. We want to make everything analogous to the classical theory on the upper half plane. Okay. That's why everything looks so weird and strange. Really, the right way to do this is to do it with adelic automorphic representations. Then you can sort of guess what the answer should be, and whatever you guess is correct. You see, that's the right way to think about it. But I have no time to explain that today. But I mean, I should give some advertising that I have a new book on adelic automorphic representations. And that's really the right language. If you do it adelically, then the functions that you see are exactly what you expect them to be. Everything is what you expect them to be. When you translate them into some classical language that's very nice for GL1 and GL2, things look a little bizarre in higher rank. You can't really, you don't really see what's going on in the correct way. When you're on the representations, adelic representations, it's like you're on the top of Mount Everest. You see everything clearly. But it takes effort to get to that point. It's not so easy to climb up there. Yeah, but I strongly recommend if you want to do the next generation mathematics, you have to get to that point. What? Degree 9. Degree 9. Okay, so let me tell you, how much more time do I have? 15 minutes. 15 minutes. So let me tell you what we can prove for these L functions. Okay? So I'm now going to just state theorems that we can prove. So this is now all joint work with Alex Kontorovich. And I want to state what we can prove for this family. So we're going to be looking at, we're going to let phi vary over all Moss forms on GL3, and we're going to look at this family of L functions. So in the Katz-Sarnak conjectures, there are no weights. They don't put any weights. We have to put in some weights, unfortunately. But it's possible to remove those weights later. But let me give you the results with the weights. So the weight that I need is, so t is some variable going to infinity. T is going to infinity. And v is v1 and v2. We can think of it as it1 and it2. These are the spectral parameters that, these are called the spectral parameters. Okay? And I need to construct a function that counts eigenvalues up to a certain point. So there's something called the Langlands parameters. So alpha 1 is v1 plus v2. Alpha 2 is minus v1 plus v2. And alpha 3 is minus v2 minus v3. And the eigenvalue lambda is given by 1 minus alpha 1 squared plus alpha 2 squared plus alpha 3 squared. So on GL, here it's equal to this. Okay. This is the eigenvalue, and I'm looking at Moss forms where del phi is lambda phi. Okay. What? Oh, v3 is v1 plus v2. Sorry. Right. And I'm now going to construct a test function. My test function is h sub t of v. And it's defined to be equal to e to the alpha 1 squared plus alpha 2 squared plus alpha 3 squared over t squared. So this is counting, this decays when the eigenvalue is bigger than t. It basically, it starts to decay rapidly. It's basically counting eigenvalues bigger than t. So we first tried to do everything with this function, and it didn't work. So we had to modify this function. So the modification is as follows. It took us a year and a half. We tried various modifications, and we finally found one that worked. It took a long time, but this is the natural thing. I'm going to take r to be any number bigger than 10. We can do it as long as r is bigger or equal to 10. So it's 2 plus r plus 3 nu j over 2. And then gamma 2 plus r minus 3 nu j over 2. This whole thing will be squared. And then we divide by the product j equals 1 to 3 of gamma 1 plus 3 nu j over 2 absolute squared. Anyway, this is the test that we use.
Sorry, is the minus in the exponent?
The alpha is a pure imaginary. So when you square them, you get an e to the minus. Yeah. This is roughly e to the minus lambda, roughly. Lambda squared. I mean, yeah, it's like e to the minus lambda. So I want to state two theorems that we can prove. There's one other thing that comes up. So let phi j such that j equals 1 to be an orthonormal basis of Moss forms. For SL3Z. With spectral parameters. So it's V1, and I put a little j and V2j. So each jth Moss form has a V1j and a V2j. Then, here's the theorem. So this is Kantorovich and myself. All j, I have aj, n1, n2, and then I have this weighting function, ht of vj. And I have to put in, unfortunately, another weight, which I'll tell you what it is in a minute. I'll tell you what this is. Then we have an asymptotic formula for this. So this is equal to so this function is 1 if n1 equals 2, otherwise it's 0. Otherwise it's bounded. I mean, if n1 is equal to n2, it's either 1 or something bounded. And well, maybe it's better to write it out explicitly. There are two cases. When n1 equals n2 and when n1 is unequal to n2. There are two cases. In this case, I get bounded by n1, n2 to the 6th over t squared. If n1 is not equal to n2, I get this. So I get a lot of cancellation. But when n1 equals n2, then I get basically the expected thing. I get summation ht vj over lj over j. And then 1, and again, this same kind of an error term, n1, n2 to the 6th over t squared. So this is our first theorem. Okay. And I have to tell you what this lambda, what this lj. Here, lj is the residue of the Rankin-Selberg L function, ls vj cross vj at s equals 1. This same factor occurs on GL2. And there's a paper of Luo where he shows that you can get rid of it by partial summation in some sense. But you need a lower bound for lambda j. You need a very good lower bound. And you basically, this residue can get very large if there's a Ziegel in this situation. And you need to prove there's no Ziegel zero. And that was done by Hofstein and Ramakrishnan. But you need to know that phi j cross phi j is automorphic on GL9, and that's not known. So assuming, if you assume that that's automorphic on GL9, we can eliminate this. And then this is a very smooth thing, so we can eliminate this one also. So that's the first result. So this result is very general and will probably have many applications. So one application that we had is we wanted to determine the symmetry type of this family of GL3 Rankin-Selberg L functions. So the way you do that is we want to count these low-lying zeros. You use the explicit formula. So you can replace the sum over zeros by So you have a sum over prime. So basically you have a sum with prime power. N1 and N2 are prime powers. You see? And then you want to estimate that sum, and we use these estimates. And everything sort of works out. We have to use the Kuznetsov trace formula. And the main problem is with the Klusterman sums, with the long element Klusterman sum. But we're able to deal with it. So let me tell you in the end what we can prove. So this is the final theorem. I'll end with this theorem. The family of LS Vj LS Vj. So we're looking at this family, j equals 1, 2, with phi j Moss forms of SL3Z has symplectic symmetry type. Has symplectic symmetry type. For the low-lying zero problem. Assuming well, you have to assume the Riemann hypothesis. Luo, Ivanit, Sarnak assume the Riemann hypothesis. You have to assume Ramanujan conjecture. They also assume Ramanujan conjecture. The one additional thing is that phi j cross phi j is automorphic for GL9. That last assumption is not necessary, but then you don't, I mean, the way they define the symmetry problem, they have a sharp cut. But we can then get the same density function, but with these funny weights. So if we knew this, we could remove the weights. Anyway, thank you. Yes, so that's not a self-dual family. So the functional equation S to 1, it doesn't go into itself, and it goes to something else. You see, we need a functional equation like zeta S goes to zeta 1 minus S with the same zeta function. Yeah, if in general if you just have phi j by itself, it's not self-dual. You can still do something, but they're conjectures for self-dual family. On GL2, it's self-dual. So it's different. Oh, yeah, these functions have Euler products. Oh, yes. Yeah. It's very hard to see the Euler product or prove there's an Euler product by classical methods. It's not easy. But if you work adelically, it's very easy. You get almost the Euler product for free. Anyway, I hope I inspired some of you to start to think about other groups than GL2 or GL1.